Yeah, so welcome back again in my lecture series on analog circuit design E211. So this is lecture number 13. So this is lecture number 13, E211 analog circuit design. So we talked about various things which are used for amplifiers such as single stage amplifier. We also talked about current mirrors, and we also talked about the Bode plot. So this is one of the way to draw the frequency response and to determine whether your system is stable or not. For that, we agree that phase margin has to be greater than 45 degree. This is one thing. Other thing is that we have to make sure that it's a single pole dominant system only. So if it is single poles dominant system, that means that all the other pole, even if your system is nth order system, only one pole has to be inside UGBW, so that effective phase margin or phase offered by the system is less than what you require. Means it will be around 90 degree. If it is like there is only single pole and all other poles are much higher than UGBW, but if it is in other way around, like UGBW and your second pole are on the same place, then phase margin is 90 degree, right? Phase margin is 45 degree, and this is the place from where you can say that its stable region is starting, right? This is one of the way to interpret this. However, you can also use Nyquist plot. You can also understand this theory by doing all the analysis as you are doing in control system. However, as a designer, this is a conclusive remark which we are going to use it for the design of for the designers of any amplifier, because that is the main objective of this course, that we need to make some amplifiers which can amplify for a large bandwidth, and things will be as per our requirement. Or we want to make this op amp, we want this op amp because of one reason, that it's a one basic circuit which can be used to realize anything, any mathematical function, anything. Like if you want to convert sine wave to triangle to some sine wave or square wave, whatever wave shaping, if you want to make analog data to digital data to analog, everywhere you need operational amplifier. And this is what our main, or one of the objective of this course, to make op amp which can solve all these problems, or which will give you one tool so that you can fulfill all these applications very well. So now let's go to the next topic of understanding, which is frequency response. However, to understand frequency response, as we have studied a bit about Bode plot and we took the circuit perspective of the same, so in that case, what I am proposing here is, let's understand one more thing which is known as Miller theorem. So Miller theorem is very important. Why it is important, we are going to study that in next slide onwards. So let's start with that. So let's assume that there are 2 points or two nodes, x and y. Look at this carefully. X and y are connected through two different elements. One is the gain element and one is impedance. So what I'm saying, or what Miller says, that in such case you can decompose this impedance in two parts. One is at input and one is at output. That is what Miller theorem says. But what will be their values, that has to be derived. Here you can see that the current flowing through the impedance Z is nothing but I is equal to Vx minus Vy divided by Z, where potential X is higher than Y. That's why it has been taken that way. Vy is a reference one, right? So for the given direction of current, the current is positive and it's Vx minus Vy divided by Z. And as I told you, as Miller theorem, if you want to apply, there's only one thing we want to do. We want to decompose this impedance such that some part come here and some part come here. You can decompose in two parts. I don't want Z in between X and Y because I want everything in pi model or with respect to ground. So it's very easy to analyze and the things becomes handy rather than going into this X to Y point, finding out the current and other things. You'll realize that if it is in the pi model, it's good. So let's go with that. For that we found out that I is equal to Vx minus Vy divided by Z. But notably, one thing you have to be careful when to use Miller theorem. If node X and node Y are connected through a gain element, then you can connect some impedance and impedance can be decomposed. However, if there is no gain element or there is no gain from X to Y or Y to X, you cannot do that. It's not applicable in that case. So let's agree on that. Now let's go further. As I told you, Miller theorem says that if there is an impedance connected in between X and Y and there is a gain element going from X to Y, we can do one thing. We can decompose this impedance in two parts. One is at input side, one is at output side. And notably, when you are doing this, let's call them Z1 and Z2. And these Z1 and Z2 will help you to find out the current flowing through each of the element. So if this particular node is Vx, then the current flowing through this Z1 is equal to Vx by I1. Let's call it I1 because that is referring to Z1. Similarly, I can write down I2 also, which is equal to Vy divided by Z2. And of course, we know that the current flowing through this impedance is equal to Vx minus Vy divided by Z. We are doing this for one reason, that there is a current flow from X to Y through impedance, but there is no current flowing from in a reverse direction, as we know that the output impedance is very low and input impedance is very high, so it cannot go inside, right? And similarly, like, it cannot be reverse, right? But in case like, we can find out other possibilities maybe in a later stage, just to find out the direction and all. So now let's move ahead with these equations. So as I told you, like, there are two equations, I1 and I2, which we already found out from both the side. So what I'm saying, that current flowing through this X in this direction, I, has to be equal to the current which is going towards ground. By the way, this is also a reference point, so both the currents has to be equal. By the way, this is an assumption. This current might be changing a bit depending on the impedances. So here we can see that Vx minus Vy divided by Z is equal to Vx divided by Z1 from the first equation. And therefore, you can write down that I'm interested to find out Z. So Z1 is equal to nothing but Z times Vx divided by Vx minus Vy. Or you can write down Z1 is nothing but Z time 1 by 1 minus Vy by Vx. Notably, Vy by Vx is nothing but a gain which is AV. Let's call the voltage gain 1 by 1 minus AV. You can highlight this equation and you can keep it somewhere, because this is going to be used when you are going to decompose the, the impedance. Z1 is equal to Z times 1 by 1 minus AV. Now let's look at the other part of the impedance. So from this we can you can see that the current which is coming inside this one has to be equal to the current flowing through the Vy node. So Vx minus Vy by Z has to be equal to Vy by Z2, and that's how like we can find out Z2, which is equal to Z times Vy divided by Vx minus Vy. You can write down that Z divided by 1 by Vx divided by Vy minus Vy, right? Okay, there is one mistake, because of this node Vy, we have to consider the current going in different direction, because now it's not a reference potential. Reference potential is different, so the current flowing through this one has to be Vy minus Vx divided by Z. So this is going to give us, okay, this is going to give us 1 minus 1 by AV, or you can say that Z2 is nothing but Z times 1 by 1 minus AV inverse, right? Let's highlight this and keep it somewhere else, right? So you can keep these two equations in your mind, that Z1 is nothing but Z times 1 by 1 minus AV, and here it's AV inverse, right? So if this is the case, let's, by the way, yeah, before starting this lecture, I should have told that all these all these uh, calculations and uh, all the analysis and the understanding has been originated by a book called Behzad Razavi, the blue colored book, CMOS Analog IC Design, chapter number 6. Chapter number 6, which is actually talking about the frequency response. Now, so we have two decomposed equation, Z1 and Z2. So if there is gain from X point to Y point, and if there is an impedance connected in between, you can actually decompose same as follows. Where Z1 and Z2 are now the known quantities from here, and AV is the gain. Now, one more thing we can think about. The thing is, what if AV is infinite? So I'm saying that what if AV is infinite? If it is infinite, then Z1 is equal to nothing but Z divided by 1 minus infinity. So it's infinity, and the whole thing might be 0 if AV is equal to infinity. And Z2 becomes, so this terms goes to 0 and this becomes Z. These are also the important observation. We are going to use it maybe on the later stage. Okay, very nice. Now let's look at the illustration where there are two resistances are given, R1 and R2. Now my question is, can we decompose the impedance R1 using Miller theorem? Because there are two nodes X and Y. Between X and Y, R1 is connected. Can I decompose this, one this side, one this side? Actually, no. That is big no. The reason is there is no gain path going from x to y. If there is gain path from x to y, you can always take that, right? So this is not possible. You have to use normal KCL, KVL, or whatever the way you want to solve it. You can solve it and you can find out rest of the things. Here, decomposition of the impedance cannot be possible. Now another one. Now if this is the case, which is one of the popular thing, where there are two nodes x and y, and from x to y there is a gain. So you can write down that y is equal to minus a times x, or you can write down a is equal to minus x by y, or vice versa, right? So there is a gain path from x to y, and there is an impedance whose name is CF. So in that case, Z1 is equal to Z divided by 1 minus AV, and Z2 divided by Z divided by 1 minus AV inverse. These are the two equations which you have derived just now. So keeping those values, you can find out, decompose CF as follows. So this will be decomposed. You need to feel these values over here, Z1 and Z2. So notably, like this is capacitor, so both side it will be capacitor most likely, right? So that is the thing, because this impedance is getting divided by some quantity, so it's not actually happening at low frequency. However, if you are doing the high frequency analysis where AV is also frequency dependent, then this might not be capacitor, it might be the combination of R, L and C. So it depends, right? So that is what going to happen. But what if this AV is infinite at low frequency? So if this is infinite, then this guy becomes 0 and this guy becomes Z, if AV is equal to infinity, for the case of infinity. So in that case, this goes to 0. There is no impedance, right? Because impedance equal to 0. So for that, the capacitor has to be infinite, right? Because it's 1 by j omega c. So then it's open circuit, because capacitor becomes open, and this side, it has to be same impedance which was here. So CF has to be transferred over here. So this is one of the important observation, that if there is a gain from x to y path, and if there is an impedance connected from x to y, which is capacitor, and if I want to decompose it in the condition that AV is equal to infinity, then it's decomposed in two parts, one at input side, one at output side. At input side, you are going to see infinite impedance or the infinite capacitor. That's how it becomes the open circuit, and the output side, same CF will be transferred. So there is no point in drawing this. So you can directly decompose this to here with the fact that AV is equal to infinity. If AV is not equal to infinity, then such things are not going to happen, right? Now let's look at other part. So that illustration says that I'm connecting an impedance, which is actually here in the case resistance, from point X to point Y. Now we need to see whether there is any gain or not. So here you can see that if you are going from here to here, and V bias is a biased voltage which is going to make sure that this VB is the voltage which is going to make this transistor in saturation, right? So in that case, this is in saturation And from X to Y, if it's in saturation, it's actually a common gate amplifier whose gain is already known to us, whose gain is equal to nothing but GM plus GMB times RO, right? This is what already known to us. So there is a gain. So that's the good news, that actually from X to Y there is a gain which is using the common gate amplifier topology, and there is a resistance from here to here. So if I want to decompose it and I want to find out R in and R out, then what I'm supposed to do? I'm supposed to do as follows, that this is input side and this is output side. So this resistance is going to be decomposed in two parts at low frequency, whose values will be, let's look at our equation which says that Z1 is your input impedance, input side, divided by 1 minus AV, and Z2 is Z divided by 1 minus AV inverse. So replacing these values, what we are getting? We are getting, let's call this one as R1, and let's call this, or let's call R in and R out as asked in the question. So R in becomes, Z is nothing but R0 divided by 1 minus GM plus GMB times RO. Similarly, for the case of R out, okay, I made a mistake here. This R in, this has to be R out, and this has to be R in. So R out becomes R0 divided by 1 minus 1 by GM plus GMB times RO. So this way we can find out R in and R out, and you can replace that and you can plug it over here to make this the pi model. Okay, so now let's, okay, it's already the solution of what I've solved. Now let's move a bit further. Although this looks very easy, but let's revisit that. So in this case, I can write down the first question. It says that find the transfer function. So what is the transfer function for this particular circuit? It's V out by V in is equal to 1 by SC in divided by RS plus 1 by SC in, and that is going to give me 1 divided by 1 plus RS C in S, where S is the Laplace operator, right? So this is the transfer function, V out by V in. Yeah, you got it? So if you got this transfer function, I'm asking a simple question. You have to find out the pole associated with this particular transfer function. So we know that the pole associated with this one is, there is only one pole, and the location of pole is minus 1 by 2 pi RS times C in. If you are finding out in hertz, if it is in radian per second, you can remove 2 pi. There is no problem, right? So any of the unit you can use. So this is the pole location, and when you're going to draw the frequency response, this is actually a DC gain. So this is what you have already, where k is equal to 1. So frequency with respect to magnitude in dB is going to give you frequency in hertz, going to give you this kind of thing, where this is 0 dB, right? Notably, this has only one pole, so the phase wise, if you draw the phase, so this is, go ahead with minus 20 dB per decade, And for the case of phase, this is going from minus 45 degree at pole location, minus 90 as it's going at infinity, and 0 degree at very low frequency, right? So this is what we have studied also, and we applied here as a like circuit. So in this case we can find out in another way around also, that says that if there is a capacitor, the effective capacitor is going to give you one pole. So if there are two effective capacitor, it's a second order and you might have two poles. You need to find out those locations. So in that case, what you have to do, you have to find out the resistance associated with that capacitor, because here you can see that the pole location depends on R and C. So it's 1 by RC if I don't consider 2 pi, and if I interested in radian per second, I can do this. So I need two things. One is called the resistance and one is called the capacitance. So what I'm saying is, the technique says that find out the effective number of capacitance. So those many number of capacitance will give you those many number of poles. So in this case, we have only one effective capacitance. So you will have one pole. And if you want to find out the one pole, you need to find out the available resistance seen in shunt with this one. Or you can say that let's change this capacitor with a known Thevenin potential and find out the equivalent Thevenin current, divide it and find out the equivalent Thevenin resistance. While doing this, we are going to make all the voltage sources to 0 and current sources are open circuit, as we know. So apply that and then you can see that the effective Thevenin impedance is actually Rs. So that is going to be kept here, and in shunt in multiply with the capacitor which we were trying to formulate. Note that when we are doing this, and if you have more number of capacitor, do not consider other capacitors at that time, right? That is very crucial thing. So if there are some other capacitors are also given or going to rest of the circuit, you don't have to consider those are also open circuit, right? Those are also uh, the the possible voltage source. You need to make them 0 at that time. So those are not there, or you can accordingly you can remove it. So we need to find out only for the capacitor which you are working on. Okay, so now let's move to further. Here now I'm cascading such amplifiers like this. You can see this is one we already studied. So I'm adding such amplifiers through some amplifier A1 and A2. Let's note that there are some extra amplifiers also there. So now I want to find out the the gain of this circuit, or going from V out to V in. So in that case, V out by V in is nothing but it's a cascading of stages. So we can see that here to here, it's already we learned that 1 plus Rs C in times S. Here, going from here to here, only between these 2 points, let's call it N2 and let's call it N1. N1 by N2 is equal to 1 by 1 plus Cn R1 times S, and let's call this one as P1 and P2. So P1 divided by P2 becomes 1 by 1 plus Cp R2 times S. So as all these are in cascade through an amplifier, actually you are going to have the transfer function of A1, A2, A3 divided by 1 plus Rs C in S, 1 plus C in Cn R1S, and one more. Let's continue with the same thing. One more, 1 plus Cp R2S. So this is third order system. You can see that effectively there are three capacitors. So three are there, and you can find out the pole location respectively. So there are three poles. One is available at 1 by minus 1 by RSC in radian per second. One is available at minus 1 by R1 CN radian per second, and 1 by CP times RS radian per second. So now the role of A1 and A2 is just to make sure that if A1 and A2 are not there, what can be happen? You cannot write down straight away that 1 by rest of the pole location, because one stage is going to load the next one. So these locations will not be at the same place. Those are going to change the place. So you need to understand that when you are going to use the basic circuit theory, you will understand that the transfer function does not look like this one. It will be something else. For that you need to modify this one. So it looks like this one. It does not look like what it was there. RS by C in right. So you need to find out all of them which are loading each other actually. So you have to move accordingly. Okay. So V out by V in is not same. Just to make sure that it's not loading each other, and these are generally used in the case of like as a voltage control voltage source, so that the input impedance is very high and it's not going to load the previous stage, and whatever voltage you want, it's going to be available. So that is the main reason for adding those things. So these are the voltage control voltage source whose input impedance is infinite and output impedance is 0. So then it is not going to load, and it will help you to achieve this transfer function. Okay, so these are the things, and if they are not there, just identify what is the problem, right? So you are not going to have the transfer function which you want. Now let's go to the next level. Now I need to find out the pole location. Let's look at this circuit. This is simple circuit similar to what we have studied. Look at this. I'm just doing one extra thing. I'm adding a capacitor between M and N point and keeping here, right? This is what I'm doing. So look, here you have three capacitors, but three capacitors does not mean that there are three poles. The reason is you need to find out the effective number of capacitances, and if such kind of capacitor or impedance is coming in between point called X and Y, you need to check, is there a gain from X to Y or not? If there is gain from X to Y point, then you can apply a Miller theorem and you can decompose the capacitor, right? So let's see that. So from X to Y, of course, Y is actually, this point is amplified, so intermediate point is amplified by the point called A1 times X, and accordingly Y is larger value than X. So there is a gain from X to Y. So in that case, we can apply a Miller theorem, even though there is one extra resistance over here, but we have to check 2 points, X and Y. There Y is much higher than X and there is a gain. So in that case, you can decompose capacitor in 2 parts. One can go here and one can go here. And for that we are going to follow two equations. Z1 is equal to Z divided by 1 minus AV, and Z2 is equal to Z divided by 1 minus AV inverse. You need to find out all these things and you have to keep it here, and you can find out two more capacitors over here, right? And you can feed these values from these equations. However, what if I am saying that this A1 is equal to infinite? because that would be the case which we are going to consider in future. So in that case, this C3 is going to be decomposed in two parts. However, at the X point, it's an open circuit, and at the output side, full capacitor is going to be reflected. So you can remove this and you can keep this one here. So now the new circuit, after removing this, new circuit looks like this one. So this becomes C2 plus C3 because there are two capacitors in shunt. So this becomes C2 plus C3. So this is a new circuit. Now you can find out that there are two effective capacitance. One is C1 and another one is C2 plus C3. And if I want to find out the resistance in shunt with that one, that's very easy. For the first part, it's 1 by minus 1 by R1 C1 radian per second. That's the first pole. And another one is minus 1 by R2 times C2 plus C3. Notably, at this point, it's looking into this, it's infinite. So it's low impedance. So there is a path with respect to ground, so it's not going to load inside, right? So effectively, you are going to see only R2. And same for here. So when you are going to short this, it's only R1. We are going to practice this, maybe this time constant technique more when we are going to introduce a transistor. Okay, so this is all about Miller theorem and its usage for different illustrations, so that you can use it. Now let's understand one more place before going to a transistor. Let's have a place where it's a negative gain amplifier. So y equal to minus a times x, and because of that, because of this gain element and this is impedance element, you can decompose this into part, right? When you are going to do this, this capacitor is coming here and this capacitor is also connected here, whereas this capacitor value is Z divided by 1 minus AV and this value is Z divided by 1 minus AV inverse. You need to replace AV with A. Let's call this one as AV itself. So you have to replace Z with the impedance value, which is 1 by J omega CFS, and you can find out the location. So here there are two locations in that case, right? You can see there are two locations. So accordingly, you can have two different pole locations. So in that case, you need to find out the resistance for this case and you need to find out the resistance for this case. So if this is the case, let's call this one as C1 and this one as C2, where inherently AV gain will be taken into account. So C1, because of C1, you can have first pole location that's equal to minus 1 by Rs times C1. This is happening because we are going to keep this one short. So effectively at this node you are going to see only Rs, and note that when you are doing this, at that time this CF is not there, it's already decomposed, right? Now the interesting part happens when there is a C2. So C2 has to see other part of the circuitry. So in that case you need to see at the output of this impedance, output of this amplifier, and output of this amplifier, as it is voltage controlled voltage source, the input impedance is very high and output impedance is 0, right? So this is the characteristic of this particular amplifier. Let's simplify this. This is RS. After decomposition you got this one. So input impedance is very high, and here it's AV, let's call it AV times V in, and having some resistance, and here we have kept the capacitor whose value is, this is C1 and this is C2, right? Let's call this one as R out, and of course there was some R in, but in ideal condition this is the case. So in ideal condition input impedance is infinite, and looking at the resistance in shunt with capacitor C2, or effective impedance looking into this circuit or at this node while keeping all other effective voltage sources to 0. So this is also not going to be considered, right? So in that case you are going to see only R out, and R out is nothing but a 0 in our case, because it's a voltage controlled voltage source whose input impedance is infinite and output impedance is 0. In this case, at this node I am going to see two things, RS as well as the infinity. So in that case RS is much lower than infinity, so RS is going to be the winning term. For the case of C1 I am going to see the pole at -1 by RS times C1 radian per second, and for this case it's -1 by 0 times C2 radian per second. However, because of this 0, this is available at infinite radian per second, and this is going to be available where it is, right? So this way you can find out rest of the things. But what if this AV is equal to infinity? This is also an interesting thing, where you have resistance minus AV, and this is V out and this is V in. If there is a capacitor, we already decomposed that in two parts, but if AV is equal to infinity, we know that Z1 is equal to Z by 1 minus AV, and Z2 is equal to Z divided by 1 minus AV inverse. So in the case of infinity this becomes 0, and in the case of infinity this becomes Z. So in that case you are going to have only a single capacitor over here whose value is, let's call it C2 to be consistent mode, and this side there is no capacitor. Look at this, the one which we have decomposed, now it's same as what was here. So in between this amplifier stage X to Y we have connected CF. So at the output side CF has to be reflected. So CF is reflected here, but at the input side there is no reflection, or it's not decomposed at all. It's 0, so it's infinite impedance. So in that case you are going to see only and only one pole, and whose value has to be found out from here, right? So as you have only one capacitor which is CF, so in this case there is only single pole, and the value of single pole is available at 1 by CF times, by the way it's in minus, CF times, if I am looking at the output impedance of this voltage control voltage source, it's 0, so it's available at infinite radian per second. By the way, all these things are happening in ideal, that's why you can see something at 0 or infinite radian per second. However, when we are going to use this, you will see that of course there will be some impedance. That impedance might be 50 ohm or whatever is there. You need to keep that, and it will have some finite number, not infinite number. Maybe we will apply this theory on the amplifier stage, and we'll understand how it's impacting in terms of poles, in terms of zeros, and how it's impacting the overall stability of the system. So if the system is not stable, make sure that it has to be stable by some pole splitting or pole placement technique, which we are going to study in maybe further lectures or maybe further courses also. So thank you for today.